Hello, welcome to my talk all about the fluid. This talk is on Reynolds transport theorem, which is a theorem for calculating the time rate of change of physical quality in the control volume in the continuum mechanics, especially in fluid mechanics. This theorem has been widely used for deriving the Navier-Stokes equation on the basis of the conservation laws. The simplest example is the fluid continuity equation, which can be derived using the Reynolds transport theorem based on the mass conservation. In deriving Navier-Stokes equation, different methods can be used. The most used methods include element method and the method using the Reynolds transport theorem. The former uses the intuitive fluid element for formulating the fluid dynamic equation. For the fluid element, we can easily calculate the quality of a fluid parameter flowing in from the surface at the left-hand side and flowing out from the surface at the right-hand side of the element. Thus, we can build the dynamic equation in a very direct way based on the principle of conservation laws. However, in such a case, we must use a special derivative named substantial derivative or material derivative. But it would be a problem, especially for compressible flow, in which we must use the substantial derivative carefully. While using the Reynolds transport theorem to derive Navier-Stokes equation is easy, but the principle behind the Reynolds transport theorem is not straightforward. This is why we need to derive the theorem, so we can understand the principle behind the theorem. This is the purpose of this talk. What is the Reynolds transport theorem? Reynolds transport theorem is a theorem can be used for calculating the time rate of change of quality of a physical parameter, especially in fluid mechanics and the large deformation solid mechanics. Principally, Reynolds transport theorem works on the whole fluid domain of interest, also called the fluid control volume for the whole fluid domain. As seen in this figure, the black line CV is the control volume, which would be in a manner that we can avoid to use the substantial derivative directly. Hence, the choice of the control volume must be different from the fluid element. Reynolds transport theorem calculates the transport of the quality of a physical parameter using the control volume. This includes the change of the quality within the control volume and the quality flowed in and flowed out of the control volume due to the fluid flowing motion, such as dilatation, notation, or shear deformation. The Navier-Stokes equation can be directly derived using the Reynolds transport theorem, together with the basic conservation laws of continuum mechanics, such as law of conservation of mass, the law of conservation of linear momentum, or the law of the conservation of energy. To derive Reynolds transport theorem, we can consider the fluid domain or the control volume. At the time t, the fluid volume is represented by Vt and its closed surface St. We can imagine at the time t plus delta t, the volume would become Vt plus delta t, and the enclosed surface would be St plus delta t. Here we must note the fluid volume change with time is not the motion of fluid domain or the control volume. Principally, the control volume would be fixed in the space, but due to the fluid deformation, the fluid volume can be changed. So, the volume V would be a function of the time only. The volume integral of a physical parameter, or the quality of the physical parameter, or simply called quality, would be a function of time only. As this, even though the physical parameter is the function of spatial parameters r and the time t, but the volume integral is the function of time only. Here, we use scalar V to represent the fluid volume. So, the time rate of change of the volume integral would be same regardless the derivative is the substantial as this or the normal as this. The reason for this is because the integral is the function of time only. It's independent of the spatial parameters x, y, and z. So this is why we see both expressions in different textbooks. And we can understand this. The system of the whole fluid is very similar to the system of a solid in principle, even though the fluid inside the control volume is very complicated. But the overall behavior of the whole fluid would be similar to the solid dynamics. For convenience, we can define the quality I as the volume integral of a physical parameter f. This is defined quality. Here, both the volume V and the volume integral I are function of time only. For example, we can define the following qualities. The fluid mass, if we take F equals to the fluid density rho, we have the mass of the total fluid. And we can define the fluid momentum as this. If we take F equals rho times vector V. Here, vector V is the fluid velocity. The Reynolds transport theorem is for calculating the time rate of change of the quality of F. At this, the question is, what is the result of the time rate of change of the quality? So this is the Reynolds transport theorem for giving the formulation to calculate the time rate of change of the volume integral of a physical parameter f. Here, the increment of the defined quantity I of the time interval delta t given by this. The increment for the defined quantity came from two different changes. The change of the physical parameter F and the change of the fluid volume V. So we can calculate this using the Taylor series and keep the first order term and drop all the higher order terms. We have this for the volume and for the physical parameter F. And we can also obtain the result for this change in the physical parameter in the time interval delta t. So for calculating the increment of defined quantity I over the time interval delta t, we can separate the integral on volume. So we have this expression. If we reorder the formulation, we have this. And we can further write the formulation as this using the formulation increment of the physical parameter F. So we have this equation. The increment of the defined quantity I is made up by two parts. The first part is due to the change of the physical parameter F within the control volume, and the second part is the change due to the volume change delta V. Look at the figure, we can see the change of the volume delta V can be calculated as a small surface ds moving in its normal direction n at the velocity un in the time interval delta t. Thus, dv is given as this. Therefore, we can change the integral on delta v, this, into the integral over the surface S as this. Now we can obtain the time rate of change of the defined quantity I as this. This is known as the Reynolds transport theorem. Basically, the surface integral can be simply understood for representing the transport of the quantity of F out of the volume V as a result of the change of the fluid boundary S. Here, because of the fluid velocity. Now we can do some more derivation on Reynolds transport theorem. We can use the Gauss divergence theorem. So we can change the surface integral into the volume integral. So we have this Reynolds transport theorem. This is the form of the Reynolds transport theorem, which is used for deriving the Navier-Stokes equation, including the continuity equation based on the mass conservation, the moment equation based on the Newton's second law of motion, or the momentum conservation, and the energy equation based on the energy conservation. If we take the physical parameter F as the fluid density, then the defined quantity is actually the fluid mass. Therefore, within the control volume, the fluid mass would be a constant. Thus, the time rate is 0. By employing the Reynolds transport theorem, we can easily obtain the integral continuity equation. And this is the integral continuity equation. And from this equation, we can easily derive the differential continuity equation. And this is the form we can see in many textbooks. And this is the universal continuity equation for both compressible and incompressible flows. If the flow is incompressible, its density would be a constant. Then we could have a simpler continuity equation as this for incompressible flows. For the fluid moment equation, we can take the physical parameter f as rho times the fluid velocity vector v. As such, the defined quantity would be the total momentum of the fluid. Based on the Newton's second law of motion, the time rate of the change of the fluid momentum would equal to the total force acting on the fluid, including the body force, this, and the surface force, this. Here, vector F is the body force density, and the tensor T double arrow is the total tensor of the fluid. Applying the Reynolds transport theorem to this term, we can have the moment equation as this. Now we can apply the Gauss divergence theorem for this term, so we can change the integral of the surface into the volume integral of the tensor divergence. So we have the integral equation for the momentum. From this, we can easily derive the differential moment equation as this. Here, double vector v is actually a tensor. In this slide, we can carry out some mathematical manipulations for the moment equation together with the continuity equation. The continuity equation in vector form is as this, and we can write this continuity equation in Einstein summation as this. Here we have two subscripts j, which means the summation as this. So for the moment equation, this is the moment equation in vector form. Its corresponding Einstein summation is as this. Now we can use the rule of calculus. We can obtain the equation as this. And the first term becomes two terms in the square bracket, and the second term in this moment equation, we have two terms as this. So if we reorder the equation as this, so we can see inside the square bracket, it's actually the continuity equation. So it is 0. So drop the first term in the left hand side, we can have this equation. If we write this moment equation back into the vector form, we can have the equation as this. Here we can see the fluid acceleration term given by the substantial derivative. And we can also see this moment equation would be same for both incompressible and compressible flows. The difference for incompressible and compressible flow is whether the density here is a constant or not. For incompressible flow, the density is a constant. And for the compressible flow, the density is not a constant. It would be the function of the spatial variables x, y, and z, or the time t.